In this video, we're going to look at Pauling's rules 3 and 4, and we're going to combine these because rules 3 and 4 do the same thing. They are both about minimizing cation repulsions. So minimizing cation repulsive forces. And if we can minimize those forces, if a crystal can do so, then that crystal structure is more stable. So rules 3 and 4 are related in this way. Rule 3 is really about geometry. Here's a diagram from the online textbook by Dexter Perkins, and he shows a cation here in blue that is coordinated with 4 oxygen atoms. Now, those tetrahedra can share various polyhedral elements. This is referred to as a polyhedron. And then when we talk about so-called polyhedral elements, what we mean here are these are going to be the corners or edges or the faces of these polyhedron. So in this polyhedron here, it has 4 faces. That's why it's referred to as a tetrahedron. So when we talk about hedron, we're counting up the faces. Tetra is Greek for 4. And then it's got 4 corners also. And then it's got 1, 2, 3, 4, 5, 6 edges. And we can link up these tetrahedra by doing various things. We can leave them completely isolated. So we can have a tetrahedron here and another tetrahedron here. And the way they might be linked up is there might be some other atom that bonds those two together. And that atom might be in some other kind of polyhedral arrangement. So in between these, there might be, let's say, an octahedron. So we can have an 8-sided pyramid here, not very artfully drawn, but we can have an octahedron here, and then it could be sandwiched in between 2 tetrahedra. So in this case, these 2 tetrahedra are not sharing any polyhedral elements at all. But another way that they might be linked is instead of by being connected by an intermediary here, they might be linked here by sharing corners, or they can share an edge, or they can share a face. But as we increase this level of sharing between just a single oxygen atom or 2 oxygen atoms or sharing 3 oxygen atoms, as is the case here, we're bringing the cations closer and closer together. This is very nicely done in this diagram here, where you could see that you've got a certain distance here. That distance now would be a little bit smaller here, and then the cations would be closer still in the face sharing case. So rule 3 is really about the geometry of these guys, that if you have cations that are highly charged, and that segues into point 4, then it's going to be increasingly less likely that you would have corner, edge, or face sharing. And this would be the least likely of them all because it brings those cations in close contact. Now there is a little bit of shielding. You could see that here. Those 2 oxygen atoms, this guy here and here, are allowing a little bit of electronic shielding between those cations, but it's not perfect shielding. So those cations can see one another. There'll be a Coulombic repulsive force, and they would push those apart. You might imagine those being split away from that edge so that they would share corners instead of an edge if we were happen to force them into an edge sharing arrangement. It would be unstable and it might unfold itself into something like this. So let's erase the board and take a look at number 4. So rule number 4 is a corollary to number 3, and that says simply that the sharing of polyhedral elements, so sharing of polyhedral elements will be especially unfavored if the cations are highly charged and have a small radius. So cations highly charged and small radius. This is way too much writing. Let's rewrite this. Let's think of it this way. Let's write it in mathematics. For the case of charge, we can call it z, and for radius, we'll call it r. Actually, in Pauling's rules, he talks about z, which is charge, and that would be over coordination number. But these two things, radius and coordination number, are related. You can go back and take a look at rule number 1, which is about radius ratios. The smaller the radius of the cation, then the smaller the coordination number. This one here is also sometimes referred to as so-called field strength. Let's get rid of all this writing. If we have a tetrahedra here, and we have another corner-sharing tetrahedra here, here's the back edge of it there, and we have some cations that occupy the center of these guys. So there's an atom here and an atom here. If these atoms are especially high in charge, let's say you have a phosphorus atom with a 5+ charge, then it's unlikely that you would even have corner sharing, and so this would be an unstable arrangement. With silica, with only a 4+ charge, that could occupy both of those. With silica tetrahedra, it's a highly charged cation, so there's not much in the way of face sharing or edge sharing, but you can have corner sharing. So corner sharing is allowed here, and there are many examples of that. The silicates are a great set of examples, but when you get something that's of sufficiently high charge, like phosphorus in a 5+ state, then even corner sharing would not be likely, and so for the case of phosphorus, we would have separate tetrahedra, as we drew earlier, and then they would be connected to one another through some intermediary. So you can think of, let's say, an octahedron out here, and that would have some other cation in the middle of it. So this is a 6-fold coordinated fellow with 8 sides. We have an octahedron, tetrahedron, tetrahedron. That would be a much more likely case of coordination for something where a highly charged phosphorus would be in the center. So that's the gist of rule number 4. That rule number 4 says rule number 3 applies, especially when you have highly charged cations like phosphorus.